Hi guys, so I thought today we could go over chapter 10, Radical Reactions. I know I might be publishing them a little bit sooner, is that I did wanted to get chapter 9 and 10 done early so you have enough time to study for them and to be able to cover, the early topics beforehand. Also for myself to have a little bit more time to study for my finals. So I think after this, after you're done with at least with this video, to the final, I feel like you should, if you're not really like your forte is not really like the exam 1 content, exam 2 or exam 3, I will believe for you to go back to those, because you're possibly gonna get like a good 5 to like 6 questions from chapter 9 and 10. But I feel like you need like a stronger support from the first chapters rather than the later chapters. So I would really try to reinforce exam 1 and 2 mainly, and then try to get exam 3 and chapter 9 and 10. So, but let's get started. I feel like this chapter is a little bit like less stressing than other ones we've been doing. This is kind of like a little bit of an easier topic, so I feel like it won't be really overwhelming. So radicals. A bond can be broken into two different ways. We have heterolytic bond cleavage, and we have homolytic bond cleavage. So then, as you can see in heterolytic, like for example, we're breaking this bond right here, and then we're putting the two electrons on one molecule. Like you can see the two electrons are going this way. In a homolytic cleavage, we are breaking a bond as well, but one electron is going one way, and then another electron is going another way. That's why when we only move one electron, we only use a fish hook, while when we move two electrons, we use a double barbed arrow. So notice how, like I said, notice how we use two different arrows. So a single barbed arrow, like we said, like this one, is mainly for radical reactions. We only move only one electron, while with a double barbed arrow, it's mainly for the regular reactions we've been using or we've seen previously, in which we move the lone pairs, we move two electrons. So how does the stability work for radicals? So the stability works the same as carbocations. Therefore, a tertiary radical is more stable than a secondary, which is more stable than a primary radical. So then let's practice. So then let's rank the following radicals in order of increasing stability. So then let's see. So then this one, it has 1 and 2 metal groups, or it has 2 carbons. So then we have a secondary in here. In here we have 1, 2, and 3 carbons around it. So we have a tertiary, and in here I only have 1 carbon around it. So that makes it a primary. So then we said that in order of stability goes from tertiary to secondary to primary to metal. So then this one will be my most stable. And then let's see, this one will be my least stable. And this is like my middle. I didn't do it like this just because I didn't want to draw the molecule. So we can do that instead of ranking. We can just do like most stable, least stable, and then middle if you don't want to like just draw the molecule. Okay, perfect. So then we first have to determine what is each one is, whether it's primary, secondary, tertiary. So then here I have one carbon group, so it's gonna be primary. This is gonna have 1, 2, and 3. Therefore, it's gonna be tertiary. And here I have 2 carbons around it, so this is secondary. So again, stability for radicals, it goes tertiary, secondary, primary, metal. So then my most stable, it will be the tertiary. My least stable will be my primary. And this is my middle. So resonance structures. I know, I'm so sorry for you guys that struggle with resonance structures. I promise if you're taking OChem 2, after doing OChem 2 is a lot of reactions, and if you try to actually understand the mechanisms of them, you draw a lot of arrows, and it helps you a lot on understanding resonance structures because you're constantly drawing movement of electrons. So then resonance structures of radicals. So bad news, I know. Resonance structures of radicals, they take in more than one arrow since we are working with an unpaired electron. Very similar to regular resonance structures, but more arrows. So then if you think about it, if you look at this, technically it looks pretty similar to what you are familiar with. It's just a lot more arrows involved, right? So then let's see. What basically happening is here is that since we're just moving one electron, so then one bond is made of one bond equals 2 dots technically. So then in here I have one dot, so then, or one radical technically, and here I have one radical. So then if I put it in, I have half a bond. So I'm gonna need to break this out. I'm gonna need to break this bond and maybe get half of that bond to, half a bond plus half a bond, I get one bond. So then in here I am able to make one whole bond, and since I only have half a bond in here, it's just gonna come out as an electron, or like as a radical on the other side. And why I don't put it in here? Because of the octet rule. I don't want to break any rules, so then my radical will go this way. So then again, when we're moving radicals or only one dot, we use that one. When we're moving two, we're moving lumpers, we use that. So then you can say it's technically like with what you have been familiar with, but it's a lot more arrows involved in the process. So stability 2.0. So now that we know that we can do resonance radicals, then this changes stability patterns, right? Because metal is the least stable, but now benzylic resonance stabilized is the most stable form. Stability goes metal radical, primary radical, secondary radical, tertiary radical, allylic, and benzylic. And the reason why benzylic is more stable than an allylic, for example, if you look at this one versus this one, you can see that in a benzylic, I am able to do more resonance structures than with an allylic. That's why it's more stable. So then if you're, I feel like it doesn't really matter how many, like if it's even benzylic. I think it's mainly like the more resonance structures you're able to do, the more stable it's gonna be. So then let's practice. Let's draw some resonance structures of radicals. And don't worry, sometimes it doesn't really make sense, because you're used to, using just moving just using like lumpers to move them, so it is gonna take a little bit of while, so don't stress yourself out. So then, for example, radicals is mainly about being close to a electron source. Like for example, in here I wouldn't be able to move my radical just because I will be breaking my rules. Like this one, and this one, they're just fine. They have they have a complete octet, so I'm not really gonna touch them. Or I'm not able to like break bonds. Remember that resonance structures is about moving electrons. It's not about breaking. We're not breaking bonds in resonance structures. I mean, we're breaking bonds technically, but it's like, what I mean is that we have the same molecular formula. Like for example, we're not taking away any H's, we're not taking away any carbons. Like we are breaking bonds maybe between carbon, so we can make another bond with carbon, but technically we're still having the same molecular formula. We're just representing it in another way. So keeping that in mind, that's it. So I'm gonna do half a bond in here. Then I'm gonna do half a bond in here. Then I'm gonna do another half a bond in here on this side. So then half a bond with half a bond, I am able to create a double bond. And then my half a bond, if I put it on a carbon, it's gonna be represented as a radical. So I'm taking that in mind. I'm not really gonna put it on this way because I will get the same molecule. So then I can see that my radical right here, it can interact. My radical right here, it can interact with this double bond. So then I'm gonna move my radical and try to create a double bond. So then I'm gonna break this bond that's next to it to create that double bond with my radical. And then I'm gonna put a radical on that other carbon. See, and that will be my resonance structures for that one. So it's technically like, it's kind of like we're doing like, we're breaking one bond and we're creating a new bond with those radicals. It's technically that. So, and I believe in you. I believe you can do this one right here. So then let's see. So with the knowledge that we did before, so we're not we technically don't have any like double bonds around this area, so we cannot create a new like a double bond from that one. But I feel like we can break this bond and then we can make we can get half a bond that's gonna go this way and half a bond that's gonna go this way, right? So then if I go this way and then I break this bond and then do a half a bond with this one, and then I get the other half or the leftover and I put it on the other side. then I am able to create this structure right here. See, it wasn't that bad. So we have to be careful. So then abinyl is radical if not resonance stabilized, no resonance structures. Therefore, a abinyl radical is less stable than a primary radical. So then this is a abinyl radical technically. So technically, if it's like position, the radical's position on the double bond, we're not technically able to do any resonance structures with it. So then what it's saying is that technically, if we have a radical positioned on the double bond, on the carbon double bond, then it's gonna be less stable than a primary. Like, it's gonna be less stable than a primary radical. Because we're not technically able to do any resonance structures with it. So then patterns in radical mechanisms. Good news, there are no rearrangements for radicals. So then, for example, you know that with carbocations we're able to do like our hydride shifts or metal shifts. So with radicals we don't do that. So there are still 6 different kinds of arrow pushing mechanisms for radicals though. The first one is homolytic cleavage. I want to remember this one. Homolytic cleavage requires a large input of energy. This energy can be, I don't want to confuse you guys. So. Homolytic cleavage requires a large input of energy. This energy can be supplied in the form of heat, which is shown as a triangle, or light, which is shown as HV. So it's what we've seen before, homolytic cleavage. So technically we're just, we're breaking a bond and we're putting an electron on each molecule, only one. That's why we use our half an arrows. And to be able to do these reactions, we normally have things like heat or light. Another pattern, addition to double bond. So it's a radical adds to double bond, breaking the double bond and generating a new radical. That's at least how the book called it. That's the description the book gave it. So basically what we're doing for this pattern is, like you can see, we're breaking this double bond and there's no presence of double bonds but only single bonds, right? So instead of doing a double bond, we're breaking this double bond and then we're getting we're making a half a bond. And then with the radical that it has, this molecule, we're doing a half a bond. So then we can create a new bond between this carbon. And since we have a leftover half a bond, we just put it on the other side. And we create a radical. So hydrogen abstractions. So entire hydrogen atom is being transferred from one location to another. So then basically we're breaking this bonding here. We're putting half a lumper on the R. And then you can see, since we're doing a hydrogen abstraction, we're moving that hydrogen to another molecule. So then that leftover electron from that hydrogen is gonna go to that other molecule that has a radical to create a bond between them. And that's how that hydrogen was moved from one side to another. So halogen abstraction. A radical can abstract a halogen atom, generally a new radical, similar to hydrogen abstraction, but this time the halogen is being moved. So it's very similar to what we did before. So we're just breaking a bond. Half of that bond is gonna go one way, half of that other bond is gonna go another way. Since we're moving that halogen, that half of that halogen it's gonna go to create a bond with this other molecule that has a radical. So that's how that halogen ended up being moved from one side to another. So elimination. So it's just the creation of a double bond. So technically we have this bond, right? So we're gonna break it. We're gonna have a bond to make a radical, and then have a bond to create one bond. To create have a bond, we have a bond in here, and then we have a bond in here. So we're able to create a double bond. So coupling, this one's pretty easy. The radicals join together to form a form. So we have half a bond on one side, and then we have half a bond on the other side. So then half a bond with half a bond, we're able to create a bond. And these are all the patterns we just went over. So you don't really need to know the names and that stuff, but I feel like you just need to get familiar that you're able to do those patterns technically. So then let's practice. Let's draw the appropriate fish hook arrow for each of the following radical processes. So what I would advise you is technically like just draw it like this, what's going on. That bromine regular state, it has 3 lumpers around it. So we'll have something like this, right? And what they want is this. So then what's different? So then it seems like this one we have a bond in here, right? So it seems like we broke this bond in here. It seems like we broke it. Oops. So then it seems like we broke it. So then we're possibly gonna do half a bond in here. And half a bond, it's gonna go on this other side. But I first want to see what else happens. So then we got that right. Okay, so then it seems like the leftover bromine, and then that radical, they ended up creating a bond between them. So then we can get this radical, and then we can get this half a bond. We can get this half a bond and then combine them together. Because, we're trying to create a new bond, so we're gonna get that half a bond from that bromine and then half a bond from this radical. So we can create this bond between that radical and bromine. And then you can see that we ended up creating that radical that's position on bromine. Okay, so you can try it on your own now. So like what just went before, I feel like it's way better when you're able to visualize all the lumpers and everything. Okay, so this one's pretty similar to what we just went over with. So then my bromine ended up with a radical next to it. So then we have half a bond in there. And then we can see that we created a bond between hydrogen and the radical. So then the radical is gonna go it's gonna go this way. And then that other half a bond is gonna go this way. So we ended up creating a bond between them. And that's how we ended up with the radical on that other bromine. So the main getaway from radicals is that there's 3 categories. So we have initiation, when there's like three steps technically to radical reactions. So we have initiation, when radicals are created, as you can see here. We break a bond and then the radical is created. Propagation, the location of the unpaired electron is moved from place to place. So technically like the original the original position of the radical is not on that where it was originally located at. Like you can see in here, it started at X and then it ended up on this carbon. Here it started at S and then at R. Here it started at R and then it ended at X. And here it started at carbon and then ended at X. So it's technically like you can see that radical moved from one place to another, place to place. And then termination step is when the radical annihilate each other and they ended up forming a bond. So I feel like you have to get familiar with those terms just because on the final, that's a final question actually. At least in my case, I got something like, look at these steps. Does this step represent like a propagation step, or does it represent a termination step? Or maybe like maybe this step doesn't represent any of them. Like, does this represent the three categories of radicals? And if it doesn't show any initiation, propagation, termination, then that answer is wrong. So chlorination of methane. So it's basically what it says, chlorination of methane. So I feel like it's way better if it's like spread it out. See, so technically this is a chlorination of methane, technically. So here we have methane, and we're putting a chlorine on it. Chlorination of methane. And so this is a radical reaction. So then they're not technically gonna ask you to technically know like the mechanism of how does it work, but they do expect you to understand that this is a radical reaction, so there's initiation, propagation, termination steps from that. I mean, if you wanted to, we can just go over it just quickly. So you can see here we broke that bond and we went from radical to radical. And then in here, so then we broke this bond thing here. Then we created a radical and put it on that carbon. So then we're able to create that, that HCl that we got in as one of our products. We're able to create a bond between them. And then afterwards we have another Cl. And then we have a radical that we created in here. So we create a bond between this one, and that's how we get HCl. Then we have our termination step, in which, all the radicals are annihilated. So then you can see that we're combining all these radicals in here. But technically, overall, what the reaction does, like if they ask you like what's your product, like if you're giving excess Cl is present, then you get polychlorination is observed. So if you start from here and you get like excess Cl, then you would end up with something like this. but it's like a stepwise reaction. So if you just get ClHB, then you get an extra one. Then if you get ClHB again, you get two. You get ClHB, you get three, and then if you get another one, then you get 1, 2, 3, 4. So it's just addition of chlorine to methane. So again, radical initiators. Energy is required initiate to initiate a radical reaction. Like we said, we need either heat or light to be able to break a bond and make radicals out of it. And that's how we get two chlorine radicals, because we broke that bond and we get half a bond this way, half a bond in this way, and we get two chlorine radicals. And again, like we said, that energy that is used to break that bond can be shown as heat or light. So like selectivity of halogenation. So there's a reaction called halogenation. So for example, where propane goes under radical halogenation, there are two possible products. So for example, we could get a radical in this area, we can get a radical in this area. Like we could add our halogen this way or either this way. So we technically should be able to predict what the product distribution should be based on the number of hydrogens it has. But actually, this will be the actual chemical rates based on the heat charge of how much energy each one gives off, or which one's more stable technically. So for chlorination reactions, they will prefer like the most steric position. Chlorination reactions, they prefer they're 65% on the least steric, while on bromination reactions, they're on the most steric. Like you can get a combination of products, but this one is more stable. While in bromination reactions, they're more selective and they prefer the more steric. So chlorination reactions are less selective than bromination reactions. And here you can see the rates between them. You can see that in fluorine, you would technically get like a combination of products. Same in chlorine, but they would rather prefer technically a least steric than a more steric. And then with bromination, you can see a big change. Like you could still get for chlorine like a combination of products, but you will highly likely see it on the least steric place. While for bromination reactions, they prefer the most steric. And you can see that it's way faster at 1600. So then remember, monobrominations, they're more selective. So then they will want like the most steric place. So let's predict what will be the following products for that one. So then since we said monobromination, they're more selective. They want like a more steric area. So then my most steric side, it will be this one, right? So then I will add my bromine on that area. And then on this side, you'll be like, oh, okay, then I would add it to my most steric. Not really, because of the octet rule. So then my most steric, it will be on this one right here. So then you do have to keep in mind of that. Okay, perfect. So then you can predict the product now. And I think you got this one. So I think like the most steric that doesn't really break the octet rule, it will be this side, right? And this one would end up being our product right here. Okay, so there's a little bit of stereochemistry, but it's not really that scary. So then stereochemistry of halogenation. Sometimes when we do radical halogenation, we might end up creating a new chiral center or doing halogenation in an existing chiral center. For example, if butane undergoes chlorination, we can get two products. One of them ends up creating a new chiral center. That new chiral center would end up creating a racemic mixture of products. So then technically, if we ended up creating like you can see in here, we created a new chiral center. So then we just didn't get we just didn't get just as R or S, we get both of the products as our products. And remember, chlorination, they're not that selective at bromination, therefore we get multiple products. And halogenation at an existing chiral center. And if we do halogenation, we would still get racemic mixtures of products. So if we do like bromination, chlorination, like at an existing chiral center, then we could get like just like a mixture of products. Like we could still get its R and S. Now, what if there are two chiral centers? If one interacts and the other does not, we end up creating diastereomers. And that's basically it, technically. Like, but you don't understand that why it ends up creating diastereomers. So remember that enantiomers, it was when we had like the complete opposite. So the stereomers is like at least one thing changed. So then in this case, say one thing stayed the same. So then in here we have like different like stereochemistry factors. Like we have this one, and then we have this one in here, and then we have this one in here. So this one doesn't really interact, so it stays the same. So at least one stays the same, and this one changes. So then this one stays the same, but this changes in here. So then we have diastereomers, right? Because at least one thing stays the same. So then predict the stereochemical outcome of radical bromination of each of the following alkanes. So then bromination, we want it to be on the most steric area without breaking the octet rule. So I would technically feel like I would add my bromine in here. So I'm gonna put this on a dash, I'm gonna put this on a wedge so I can represent that there are different configurations. So luckily this wouldn't be able to be a chiral center, right? Because we have the same groups connected in here, so this is not a chiral center. So we only have one chiral center technically. So if we only have one chiral center, and we're just flipping this chiral center, we're just flipping the configuration of that one, then technically we just have right here, we just have enantiomers. Remember that we don't have more products because we're doing bromination, and bromination are more selective. Okay, perfect. So now it's your turn. So we want the most steric area, the most bulky area without breaking the octet. So that one will be this one right here. And I feel like we don't have any like chiral centers, because this one cannot be a chiral center, this one either, this one either, this one either. So we only have one chiral center, which is quite nice. So therefore we just be creating enantiomers. So I'm gonna put my bromine on a dash, and then this another one on. I'm just gonna flip this one on a dash, and my bromine on a wedge, and then I have enantiomers. Okay, so allylic bromination. Let's look at reactions with alkenes. Allylic bromination, remember? But when using radicals to prevent competition, we use NBS instead of bromine too. So this is technically like a look back to chapter 8. But I'm gonna show you a new reaction. So then this is NBSHB. So then with NBSHB, technically we are putting we're putting kind of like a radical next to like to that double bond in one of the most steric areas, and then we have like different products. So then we put it on the most no let's see, hopefully it didn't close, it didn't erase at least. Let's see. Okay, so then in here we put a radical in here, and then technically we just did a resonance with it. So then again, we're just gonna be breaking this bond. We're gonna get half a bond on this area, half a bond on this area, then half a bond on this area. That's how they did a double bond, and they put a radical in here. And then where that radical is positioned, they just added a bromine to that. That's called bromination. So then predict the monobromination product that's expected when each of the following compound is treated with NBS. So then let's see. So then I technically cannot put it in here because I will be breaking octet rules. So I would rather put it on this area. And then I will try to create a resonance structure from it. So I will do half a bond in here, half a bond in here, and then half a bond in here. And if you technically think about it, this one ends up looking pretty similar to that one. And yes, it's because they're the same molecule, so they both end up leading to the same answer. But just I would still recommend you to do your resonance structures on other molecules, just because sometimes it's not gonna be as nice as that. And then we're just gonna add our bromine to that radical. Okay, perfect. So try it on your own. So remember, just put the most your radical next to the most steric place that doesn't really break the octet rule. Do your resonance structure, and then just add your bromine to that. Okay, perfect. So then technically, if you think about it, both sides will look the same, so it doesn't really matter if you started from here or from here. So now I'm just gonna put it on this side. Let's see, I'm gonna do half a bond in here, half a bond in here, and then just gonna put my leftover in here. Okay, perfect. And then let's see. And then I would just draw my original positions, and here I have my bromine. Then here I have my bromine. That's it. And that one will be our final answer for that. So autooxidation and antioxidants. So in the presence of atmospheric oxygen, organic compounds are known to undergo a slow oxidation process called autooxidation. So basically, if you look at this, we still have our metal groups, but we're just adding an OOH next to it. So it's technically like, remember what we did? Next to a resonance structure, we put it to like the most allylic position. So our most, not most allylic, more steric position. So our most steric position will be this one. And then we just added our OOH to that side. And this one again, this one is how's it called? This one is a radical reaction. So then basically what you need to know is how initiation, you don't need to memorize the mechanism, but you need to know how it works. So you have your initiation, propagation. Initiation, remember, is about the initiation step is about creating that radical, breaking that bond, creating that radical. Then propagation is about moving that radical from one side to another. Move your radical from one side to another. And then termination is when you eliminate that radical, meaning that you create a bond between you. You put half a bond, and create a bond, and you end up with a bond. So what's surprising is that we're going back to this reaction, radical addition of HBr, anti-Markovnikov. Remember from chapter 8? So we saw how alkene reacts with HBr and we get Markovnikov, right? And if we do HBr with peroxides like ROR, so our HBr and underneath we have ROR, we got anti-Markovnikov, right? So this is actually a radical reaction. So again, we just do initiation. Initiation step is about creating those radicals. We created radicals. Then we get propagation, in which we move our radical to the other side. Therefore, our radical is not on the same side it started. And then we get our termination step, in which, we annihilate those radicals and we create a bond between. So again, this reaction, I just wanted to let you know that the reaction is actually a radical reaction. So remember, this reaction has stereochemistry, right? If you create a new Carnot center, you get a mixture of products. You get the product plus its enantiomer. I already see you guys getting a little bit of PTSD from this. Product plus enantiomer. So don't forget to say that. So then again, we just add or since we have ROR, we add our bromine to the least steric place, which would be this one. And if we do end up creating we do create like it says a new chiral center, we get a mixture of products. We get it's R plus it's S. Okay, let's see, let's practice. So predict the major products for each reaction. In each case, be sure to consider whether a chiral center is being generated, and then draw all expected stereoisomers. Okay, perfect. So we just have to put it on the least steric area since we have RR, which will be this one, right? So let me put it a little bit more nicely. So it will be this side. So let me break this bond in here. Since you know HBr, we're adding the hydrogen on one side, we're adding bromine on the other side. And it seems like we're technically creating how would you say, like chiral center, yeah. Because in here if we like not on this side, but in this side we are creating one because we added our H. So then in here I have a CH3, I have a CH2, CH3, and I have a carbon bromine. So then that means I have 4 different groups. I have a chiral center. Therefore, I will have a mixture of products. And that one would be my answer. Okay, perfect. And now it's your turn. Okay, perfect. So let's predict that major product right here. And in here, there's not really a major product because we've seen that it's 50-50 if we get like a mixture of products. So it is possible to get like 2 major products. So HBr with peroxides, we just add bromine on the least steric and we add hydrogen to the most steric. So in here, we obviously don't have a new chiral center, but in here we have a CH3, we have a hydrogen, CH2, CH2, CH3. I think we do have a new chiral center. And that one will be our final answer. So then these are just some extra reactions. So then radical processes in stereochemistry. So cracking, convert large alkanes into smaller alkanes, more specifically called hydrocracking. So it's the use of hydrogen 2 with heat. And then you can see we're just breaking this long chain and we're just making little chains with that one. There still is the same number of carbons. For example, in here we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then here you have 1, 2, 3. 1, 2, 3. And then we also have reforming. So we can also use heat to cause a straight chain of alkenes to become a little bit more branched. So you can see in here we have a straight chain. And then we just heat and then it just became a little bit more branched. So some reminders. So then we've seen that a radical chlorination or bromination, well, bromination is more slower than chlorination, but this is due because it's more selective, it's more steric. remember that bromine is 100% on the steric, while for chlorines it's like kind of like 60% on the least steric, and then like 40% on the most steric. So it's kind of like a mixture of products. It's less selective. So this is just a small reaction review. That's mainly all for radical reactions. So in here we have bromination of alkanes. So bromination is more selective, like we said, it's on the most steric side. Anti-Markovnikov, like we said, H is actually a radical reaction, surprisingly. So HBr, hydrogen on the more substituted, bromine on the least substituted across an alkane. And then MBS, remember we're just adding a radical to the, like, really close to that double bond, so we're able to do resonance structures with it. So technically in here they just show one product because you will get the same product eventually, but if you're able to get like multiple products, then that will be your answer. But that's mainly it for radical reactions. So thank you so much for taking your time to watch this video with me, and I hope you have a wonderful day.